We have how-to videos, momentum example 5, conservation of momentum where both items are moving. So Fair is playing soccer against one of his students, and we're both headed toward the same ball. So, okay, here's Fair, and he's got his tie on. Apparently, that's the only part of the uniform. Anyhow, sketchy. So here he comes, and his student is running right toward him. And she's, oh, okay. And we don't care about the event itself, so I'm just going to draw this wavy line. And after the event, Fair is still running this way and still has his tie. And he's going this way, and we're wondering what has happened to his student. Maybe she was run over. Who knows? Okay. Uh, so we go ahead and list out the information. So we have mass of Fair. Initial velocity of Fair is 1.2 meters per second, and final velocity of Fair, it's going to be 0.8 meters per second. Mass of the student is 60 kilograms. Velocity of the student initially is negative 1.4 meters per second. Okay, it says this, and that's because she's moving in this direction here, so negative 1.4 meters per second. And final velocity of the student is unknown, but hopefully she survived the impact. And yes, this is actually based on a true story, and it was rather amusing, and she did survive. So initial momentum of Fair plus initial momentum of student is equal to final momentum of Fair, that's prime, plus final momentum of students. Well, we're looking for this, so we know that we cannot cancel anything out. Nothing is equal to 0, which is kind of sad, but oh well. That means we're going to be moving this guy over. And then I can start substituting in. Uh, mass of Fair times initial velocity of Fair plus mass of student times initial velocity of student minus, because we subtracted this over, mass of Fair times the final velocity, that is v prime of Fair, and that is all equal to mass of the student times the final velocity of the student, or vs prime. Now I'm looking for the final velocity of the student here, so I'm going to divide through by the mass of the student. Now some people might be noticing, oh look, it's got mass of Fair over here and here. Can I factor that out? Well, I could actually, if I really wanted to, I could try to combine these, but I'm not going to bother because that might complicate things a bit too much. It won't really speed things up, so I'm just going to write everything out. Okay, let's change colors to make it pretty. We have 125 kilograms is the mass of Fair times the initial velocity of Fair, which was 1.2 meters per second, plus mass of the student, which was, oh, I'm starting to write mass, which was 60 kilograms, times the initial velocity of the student, which was negative 1.4 meters per second, and then minus, because of this minus sign right there, minus mass of Fair, which was 125 kilograms, times Fair's final velocity, which was 0.8 meters per second, all of which, the whole thing, is divided by mass of the student, so that's 60 kilograms, and that is equal to, almost running out of room, this equation's so big, final velocity of the student. So we combine this whole numerator, we get this giant numerator up here, we work it out to be negative 34. You say, whoa, that final velocity is crazy big. No, it's negative 34 kilograms times meters per second divided by the denominator, which is still there, 60 kilograms. 60 kilograms. Tapping that into our equation, or into our calculator, we have negative 0.5666667. So let's round off. Negative 0.57 meters per second was the final velocity of the student. In actuality, she was actually kind of ended up on the ground. But she wasn't injured, so everything was fine. And she still survives today. No lawsuit. Yay.